Today I'm going to start a new section titled Dimensional Analysis, Similitude, and Modeling. Okay, so first off, this dimensional analysis is actually a branch of mathematics. Okay, and the whole point is I can organize the variables that defines my flow into sets of dimensionless groups. I'll show you how to do it. Okay, but before I go ahead with the mathematical approach, I want to talk a minute about why we're doing this. Okay, so far, if you watched all the videos, you have noticed that I obtained some algebraic solutions to the problems that I posed, right? But in some cases, this is not quite possible. Okay, the flow may be too complicated. I may have too many parameters that changes the behavior of my flow, so I may not be able to fully understand my flow with an algebraic equation. Okay, so in this case what I do is typically I go to the experimental route. So I do some experiments, try to analyze the data, fit some curves to the data, and get some equations based on my experimental data. Now the problem is experiments are expensive. Okay, regardless of what you're dealing with, experiments will take significant amount of time, money, and resources. Okay, this is applicable to academia as well as industry as well. What I would like to do in this analysis is to reduce the amount of time, effort, and money spent on the experiments. Okay, and the first approach is called dimensional analysis. So I'll start by that. So let's start. So first of all, this is a simple method of predicting physical phenomena. For instance, if I'm interested in the drag force of an object, okay, Ft typically represents the drag force, okay, and this will be a function of multiple parameters. However, in this particular approach, I want to minimize from the real life to much more manageable. Okay, let's say that I have some kind of a length. Okay, I have a velocity, and typically the fluid effects are represented by the viscosity and density. Okay, so let's say that this is the case, and again, in real life, that's much more complicated than this. Okay, the goal here is collect these 1, 2, 3, 4, 5 parameters into a smaller number. I will quantify soon what I mean by a smaller number. Non-dimensional terms, so that I can conduct my experiments faster and cheaper. And as you will see soon, these smaller number of non-dimensional terms will be a function of the parameter. In this particular case, it will be 2. Okay, so I can reduce from 5 to 2. This dimensionless groups are called the pi terms. If I have n number of pi terms, then I will write this relationship. This pi n can be represented as a function of pi 1, pi 2, pi 3, all the way to pi n minus 1. Next step is to find this n value. Okay, I mentioned that if you have 5 parameters, we're going to end up with 2 non-dimensional terms, right? However, before I go ahead and find my n value, I will have to introduce a concept to you. Okay, and this concept is called general dimensions. So what I mean by general dimensions is this is related to units. Every physical parameter has a unit associated with it. Okay, and in fluid mechanics, m, mass, length, and time, or force, length, time, is sufficient to represent flow properties. Like you to note that there's also temperature. Sometimes we may need to include temperature as well, but I will not be going in that direction today. Okay, so basically there's two units, MLT and FLT. Okay, let me give you an example. For instance, let's look at the density, right? Density is obtained by mass divided by volume, right? The mass, the unit of mass is, in terms of, if I'm using MLT system, it will be mass divided by volume will be length cube, right? So from here, I will obtain ml minus 3 as my density unit. Let me do the same analysis for the FLT system. So for that, I will use the same formula, obviously, right? But now this time around, I cannot use mass because I'm using FLT, right? So now what I need to do is I need to represent mass in terms of a force, okay? So you can see from F is equal to ma is force will be equal to mass times acceleration, which is LT minus 2, right? So from here, if I go ahead and find my m, I will get myself F L minus 1 T square, right? So then I will simply go ahead and insert it there. So it's going to be F L minus 1 T square. The volume is still L cube, right? And if I go ahead and find it, you will see that I will obtain F L minus 4 and T square. So that is my density in the FLT system. I would like you to note that I was able to accomplish this because I use something called dimensionally homogeneous. What it means is that the units on the left hand side must be equal to units on the right hand side. This is applicable for all the courses or all the physical phenomena as well.